Oh, no, no, now we're good. Yeah, it's counting down. Okay, sorry. It only records 30 minutes at a time. That's a pain.
30?
30.
Oh,
30. 30. Okay, so we've done K-maps now with 3 variables, 4 variables, sum of product, product of sum. We're not going to do 5 variables. There's one last thing we need to consider, which is sometimes we have, and we run into this with BCD, binary coded decimal, to get 0 through 9, that's 10 levels. So how many bits do we need to get 10 levels? 3 bits gets us 8, that's not enough. So 4 bits gets us 16. Well, we only need 10. What do we do with the other 6? If we're only doing decimal, we don't care. We don't care what those values are. It doesn't matter. We don't care. And so they're called don't cares. So essentially what we're going to say is everywhere that there's an input that can't happen, or we don't care if it happens, we're just going to put an X. What that means is we can use those X's to make our circles bigger, but we don't have to include the X's. So if they help us, great. If they don't, no worries. So, because again, remember the goal is always bigger circles. So here, I can use those don't cares. I could use one of them, right? I could circle that one, and that's smaller than circling the one by itself. If I come down here, I can do the same thing. I'm trying to show with this. But I don't need to do that, right? I need to get as big a circle as I can get on this one, but I don't have to get that X. The X is only here to help me if it's useful. So I'm not going to include it if I don't need it to make a circle bigger to get a 1. So let's do an example of that. Well, let's look at this. Here's an example.
For that last one, could you do either or?
Either one, exactly, right. So here's this one. Here's an example. You've got a switch that's only got 5 different possible values it can have. It can only be in one of 5 positions. You need 5 levels, so how many variables do you need? How many bits? 3, because 2 won't do it. 2 only gets you 4, and you need 5. So you've got 3 variables. That means you've got 8 possibilities. You only have 5. So 3, you don't care what happens because you're never going to get them. The switch only has 5 positions. So you know you want the output to be a 1 when the switch is in position 2, 3, or 4. And you want it to be a 0 when it's in position 1 or 5. Anything else you don't care. So we put a 1 at 2, 3, and 4. We put a 0 at 1 and 5. If we did not use don't cares, we would only have the 1s where we needed them, and everything else is 0. So without don't cares, this is what we're stuck with. This small group of 2 and this small group of 1. But if I put in the don't cares for all the values I don't care about, a bunch of those zeros turn into X's, and then I can use them as a 1 or a 0, whichever makes the most sense for me. So now this X gives me a group of 4, and those X's give me a group of 4. So I've dramatically made my circuit smaller by just using things that I'm never going to get those inputs anyway. So I can use them however I want to. So let's do an example. I think that will make more sense. So let's look at this one down here at the bottom. We call don't cares with a D because we're not very inventive. So if you list this sum of little m, those are min terms. If you add a D, those are don't cares. So we're going to put in here 4 variables. So it's a 16 4x4 K-map. So we want to put in 0, 1, skip 2, 3, 4, 5, skip 6, 7, and then remember 8 is down here. So we're going to go 8, 9, skip 10, it's a don't care, 11's a don't care, and all the rest, 12 through 15. 12, 13, skip, 14, 15. So again, the idea is we're trying to get as big a circle as we can get. We don't have to get the X's. If they help us, great. If they don't, no problem. So here, I can use these to get a nice big group of 4.
So why are we Xing?
X just means I don't care. It's input that isn't going to happen. I don't care if it's 1 or 0. It doesn't matter.
Oh, okay.
So if it doesn't matter, in this case, I'm going to count it like a 1. Do I need to circle this big long line of X's? No, because it doesn't cover a 1, yes.
Okay, I understand that bigger circles make it better,
Yeah.
but by including unnecessary inputs like the X's? does
They're
it
not
really-
unnecessary inputs, they're inputs whose value I don't care about. Means it can happen, actually it means it probably can't happen. Usually don't cares are ones that can't happen because they're just not possible as inputs. Like that 5-position switch. I have to have 3 bits, so I've got 8 levels I can encode. 3 of them, there's no way I can ever get. So I can treat them any way I want to, because it doesn't, what it means is it doesn't matter whether this is a 0 or a 1. Either one will work out for me. So I can treat, if it doesn't matter, then treat them like a 1 if it helps.
Okay.
They're just cases where typically they aren't possible to get, in which case it doesn't matter what the value is. Yeah.
Why were 8 and 9 not don't cover? Are they just not in the range that we were given?
Right, they were not 1s, and they were not don't cares.
Okay.
I just put an 8 there to remind us where 8 is,
All right.
so we don't forget to skip. All right, so what else do I see? I think a group of 4 here. What else?
On the right.
I could do these 2, or I could do those 2. Which one should I do?
The 2.
I think these 2. I could do these 2, but then I still have to come back and get that one. So you always do your 1s first, and then if your don't cares help, that's great. So let's write what, yes.
Could you do a group of 4 with the top right 2 and the bottom 2 don't cares?
Yes, that would be even better, except I still have to do this one.
And you just do a 2 on the left.
Yes, but here I get 1 term, and here, if I do it that way, I get this term and another term. End up with more terms, so that didn't help me. Yeah. So that's where the art comes in a little bit. Okay, so let's write this out this way, and then let's also write it out in terms of, so I guess I'll start with red. So that's just going to be CD. And then look at this blue line, what stays the same? B is 1, and C is 0. B is 1, C is 0. And now this term, A and B are both 0, and D is 0. So remember the name, what you're writing for the term is what stays constant for the group. So this would be A prime, B prime, D prime. If we did not use the don't cares, then this group would be smaller, so it would have more variables, and this group would be smaller because it would have more variables. So this would have been just that much. So it would have been A prime C D. But that's part of CD. Right, CD is a bigger group. So, and then this one would have been A prime B C prime. So it would have been bigger if I had not used the don't cares. Thing is I don't care what these values are. So it's kind of like saying I really have an extra ACD added. I can add ACD because I don't care if it happens or not. And so once I add the ACD to this, because it can happen, I don't care, then they combine to that. Yes?
So if you were to do it by hand, well, like without doing the graph, then the don't care.
Don't care is-
There would be no way to account for that.
Not really. No, there wouldn't be. So don't cares really are only just sort of magical when it came out. Because you'd have to look at having them or not having them, and that would be hard to write. I guess you could dot them in or write them in light gray, or I don't know, it would be hard to do.
So the don't care, is that a way to use, let's say, a standard
Yes.
component that can be used on different applications?
Right, and they're just some levels that you're never going to get inputs for, and so you don't care, and so yeah. So when we go to do the 7-segment display with the BCD, we're exactly going to end up using this. Okay, so just briefly, because I really want to finish, we need to just look briefly at XOR and XNOR patterns, because there are some. So let's look at this. XOR counts every time that there is a odd number of ones. So here's 1, 1, 1, 1, 1, 1, 3 ones. that zigzag pattern is an XOR pattern. So if you ever see that in your K-map, you should see if you can work that out. Here's one. So here, if I were to only consider the X row, then I know that I've got it when either Y or Z is 1. So this would be X and Y XOR Z. So you can see it for the entirety of the K-map, or you can just see it in one row. And that just means you and it with, so here, let's do some examples. All right, so here I think I've written them out already. So here, this one I just recognized. This is just going to be X or Y or Z. This one is different because X must be 1. So if I were to write this out, right, in both of these cases, I would just have a bunch of single circles, right? So that would be, this would be 4 minterms. This is 2 gates. If I did the 4 minterms, each one has 3 variables, that's a lot of gates and a lot of inputs. So the XOR saves us a ton. Look over here. Let's say I don't see the XOR, so I write it this way. I just circle them one at a time. So X, Y prime Z, or X, Y, Z prime. I can factor out the X. If I factor out the X, this is exactly XOR. One or the other is one, but not both. So I could skip straight to here and just write X and Y XOR Z. Okay. So I think I would like to revisit. These are more complicated, so I'm going to let you look at those on your own for a bit, and we'll come back to those in another class because we want to make sure we have time for the lab. So we'll come back to some of these, and then I'm just kind of trying to buzz through what I need to say. Minimizing by hand is hard. Tends to be prone to error. So much easier to use a K-map. Some students will use Excel for K-maps because you know how to do conditional formatting. So you can make all your 1s be a red background, and all your 0s be a green background, or whatever colors you want. And that way you can very quickly see, rather than just having 1s and 0s, it's some color coding as well. So some people like to do that. Quickly, actually I'll come back to this another day as well, so I need to come back to those 2 things. So this is something that we're not going to do in class, it's just kind of for your information for later you'll need to know. So we'll come back for these. So, briefly, again, we've talked about trade-off. So if we have, we can look at things that are 2-level implementation. The delay will be small, but the number of gates may be big. We can stagger them a little bit better. The delay will be longer, but the number of gates is smaller. So that's a pretty common thing. Here's something to remember. This is a big giant gate. I could use maybe some small, I could do a different, factor out a different way, have fewer gates but longer delay. So factoring allows us to reduce gates. For you, for lab 3, you're all about reducing gates. And then lastly, if you remember, we talked about the critical path, which is the longest path it takes. Do I need to make sure this path is really fast, no delay, if I've already got a long delay here? No, I can make this one a longer delay. It doesn't matter because it's still not as long as the longest one. So it's one of those things, don't try and optimize a piece, when you've got already something else that's longer yet. So there's no reason to do that work. Okay. And then lastly, and you can see this in K-maps, if you have 2 different functions and you circle the same ones, the same group, that means you can share that gate. You can do it once and then use it in both places. So again, just another way to shade gates. Okay, so we will come back to some of the XORs next time. So now what we need to do is move quickly to the lab. So again, let me just show you one quick thing, and then we'll get busy with Logicin. Okay. Importantly, we talked about the fact that this is not real, right? Gates don't really switch like that. This is what you would see if you actually hooked it up to an oscilloscope and you looked at the traces. Notice it's not exactly 0, and it's not exactly 5, right? There's noise in the signal. It bounces around a little bit. And then it takes some time to switch. Doesn't switch instantly. So the question is, what counts as low, right? If your noise bounces up too high, is it not low anymore? And also, how long does it take to get from one to the other? At what point in this crossover do I consider it to be high? And how long does that take? So, let me do this here. I'm trying to tape it for, I don't know if that's going to work. Okay, so we're going to look at, just briefly, you have pinouts, but you also have data sheets. The data sheets tell you everything, not just the location of the pins, okay, but much more than that. It's going to list a whole bunch of information about input and output voltage levels, input and output current requirements. So I have summarized it for you. So VOL is the output voltage that occurs when the gate is low and the output is low. VOH is the output voltage when the gate is high, the output is high. So clear? These should make some, I mean, they're all kind of named the same. Based on IEEE standards, positive current enters the device and negative current leaves the device. So that's just kind of our convention. Okay, so here it is for a NAND gate. VCC, normally we say power is 5, but it'll accept a range, 4.75 to 5.25. Input, anything below 0.8 counts as low. For output only outputs as high as 0.4. So does that make sense? Output comes out at 0.4, but anything up as high as 0.8 counts as low on the next gate. That makes sense, because that means if you get some noise added, you've got a little buffer, right? So let's look at this graphically. Here we're saying that we're going to output 0 to 0.4, but anything as high as 0.8 is going to count on the next gate as being a low. That's good, it gives us a little buffer. And same thing down here. We're going to output between 2.4 and 5, but anything as low as 2.0, 2.0 is going to count as a high. So it gives us a little bit of noise margin. Propagation delay. At some point, it's going to take some time to get from one to the next, and it's not the same. Isn't that interesting? To go from low to high takes 22 nanoseconds, but from high to low, only 15. That's just a function of how the transistors work. So, again, not a big deal for us. Are we going to notice nanoseconds in delay? I think it probably not. But you could imagine if you had thousands or millions of gates, that would accrue. So that's where it becomes an issue. And then lastly, fan out. There's a certain amount of current that comes out and a certain amount of current that's required coming in to make these devices work. It turns out for TTL devices, which is what we're using, do I have the numbers in here? I don't. It turns out that this ratio is 10. So one gate can send output, the same output, to 10 different other gates and still have enough current to run them. So we're limited to 10. If you were to use CMOS instead, the amount of current that CMOS requires is tiny. So instead of 10 gates, you could run thousands of gates from one gate. So the output of one could be sent to thousands of gates. So we just use TTL because it's cheap. And that's it. So we don't have time, right? So if time, not enough time. So you can feel free to look at that at your leisure. So it is time to start the lab. So we're going to be a little pressed, so let's try and be really on point. So we're going to start with Logisim. Has anybody done Logisim with Logisim already? Maybe. Okay, so let's go ahead and grab a computer full of Logisim, and we'll do that first, and then we'll look at testing some of our boards. And we'll close Logisim as well. Let's see. Remember, you're going to want to go to the website and actually, we're going to start branding. Never mind, we're going to start branding.
Yeah. I thought they only had 2 outputs.
Yeah.
Yeah.
I vote for we make the XOR, make circuit 2 first, just because it's easier. So we're going to make circuit 2 first so I can show you the different specific components you're going to need to use. Okay, so once you get, I'm trying to have both of them. Once you get Logisim up, actually, maybe I can make it bigger yet, right? Once you get used to using Logisim, it's really easy. It's a lot of clicking and dragging, but there's a couple of pieces that, and there is a file that I hope you guys will maybe even have already referred to, but I suspect perhaps not. There is some information on our class site that has more information about Logisim. So,
Which file are we?
what's that? We're starting a brand new file.
Okay.
Yeah.
Okay.
You did it
No, I did the that's the one.
Oh, yeah, these are JTCAGET. These ones are not, these,
JT might works on these ones.
oh, and JT might, so either one of those. Does it bring up Logisim with JT might, really?
Mm-hmm.
All right, that's my J and T. I don't know what that was. So this is what,
A will be
that one,
C
or
will be
JT might.
A or C. Then
Either one of those.
A will be and C.
You can use it for both
You go
username and
backwards.
password. These ones are different from everywhere else in the college. Okay, so when we're in Logisim, notice that some of the gates at the top you have ready access to, not and an or. Right there, and here's a pin. You've got an output LED and you've got an input pin. So across the top you have most of what you're going to need for a lot of your designs. My suggestion, so if you explore what's under wiring, gates, and so on, let's just expand gates. Not, buffer, we'll get back to buffer, and, or, NAND, NOR, XOR, XNOR, we have all the gates. If you just simply click on the XNOR, it will drop one, right? You have to click again or actually duplicate to drop another one. But I don't recommend doing that until you make some fixes first. So when you click on it, you see down here, or if you clicked off of it, you can right-click it and say Show Attributes. And if you look down here, you have a bunch of things that you need to talk about. You can make the gates smaller or bigger, so you may decide that some of your designs you'd rather have them smaller. Number of inputs is currently set for 5. We're only going to need 2, so I would go ahead and change that to 2. The other thing is the facing direction. Facing east is the way the output is on the, their normal clock direction. So it's facing east, the output. So you just go over here under gates, and you just click on the XOR gate. Oh, I'm sorry, no, either one, I'm sorry, I didn't make that clear. All right, so I'm going to change the input on this one. You can click the up arrow and just select 2. It just makes it a little bit cleaner. And then, now that I've got the one that I want, why am I stuck? Hello? What happened? Where am I? Oh, there we go, sorry. Now that I've got it this way, now you can say duplicate. So you can just do a copy and paste. So copy and paste, and now you have a second one. So I would make it the way you want first, make all the changes you want first, and then just copy and paste the gate. Notice how I've kind of staggered them a little bit, because I know that I'm going to have 2 inputs coming in here, and then this one is going to come down and into this one. So I need to leave a little bit of space. So we're going to choose this up here, the box with a green circle in it. That's called an input pin. So we're going to add a pin. Come down here, and right now it says it's facing east. That's good. Data bit 1. 3 state no. That's correct. And output no. That's correct. This is an input pin. So I can just drop it right there. Notice it defaults to 0 to begin with. Dark green is 0. Light green is 1. Just to help you see that. But and so then that is what I like. So I can either keep clicking and dropping, or I can copy and paste. Notice I'm trying to line this up so so I'm just gonna draw a straight line right to the gate. That's kind of your best thing to do. So now you're just literally gonna click on this dot and drag over to that dot. Be sure that you don't over drag, like go and drop the end somewhere you don't mean it to be. So we're just gonna connect up these two. And then I'm gonna connect up this last one. And now I need to connect up the output, right? Because that's what we're doing here. We're making this circuit. So the thing to do when you're doing this one is don't try and drag straight there. That it doesn't. So my suggestion is to drag to about like that, and then let go, and then drag the rest of the way. That way you can get the L where you want it to be. Otherwise, it pushes it all the way to the end, and it makes it a little bit harder to see. And it's harder to see if your inputs are right. All right, so now we need an output pin. A couple of different ways we could do it. We could grab this guy and put it over here. Before we do that, we're going to want it to face the other way, so I would say west. I do want it to be an output pin. I don't want it to be three-stage. So
The
now
circle one.
What's that?
The circle one
it
does
does.
the output.
I know. So it turns into that, which is exactly what this output one is at the top. Oh, except it's like I changed it permanently. I did not mean to do that. All right. So I'm going to just grab this one. So the one that's a circle, that's an output pin. Right, so click, and then just drag it down here, and then just connect it up. If you ever get a blue X, that means something's not connected. It doesn't have input. So blue X's are bad. Red lines are bad. And I apologize that we have green lines and red lines. So now we have a circuit. If all the inputs are 1, do we expect the output to be 0? I mean, if all the inputs are 0, do we expect the output to be 0? Yeah. So I would like to name these as well, though. So there are a couple of things we can do. If you click on this one, there is a place where you can put a label. So I recommend doing that. A. Label location. It tells you, so if you prefer to have it on top, you can do that. You can change the font. You can get pretty particular. So here I'm going to make this one B. I'm going to make this one C. And so now I've labeled. It's important that you label it that way rather than just adding a text box, because by labeling the pins, we're going to see that Logisim has some powerful tools that can then use it can actually refer to those pins as ABC, as variables, algebraically. We can do the same thing over here and name the output F. So
the pin with the circle around it is for output?
Yeah, so a square is an input and a circle is an output. Okay, so now if I've got ABC and I wanted to start testing my truth table, A is the most significant bit, and so that's when you can add a text box here, so this text box, and I can just put most significant bit, and then I can, there you go. I can put a text box. Oh, maybe then I type. Something is not working with mine. It must be. So if you want to, you can just put this here, just to remind yourself that that's the most significant bit. Feel free to do that. So if I'm changing this one at a time, I'm going to change my least significant bit first. So if I change C to 1, I need to be in poke. The hand with the finger is poking, so I need to poke. So if I change C to 1, I get a 1. Is that expected for XORs? Yes. If I want to test the next combination, that's going to be 1, 0. So I've got to turn that off, turn B on. Is that correct? Yes. The next combination would be 0, 1, 1. Is that correct? Yes. 2 1s should not give me a 0. XOR should only give me a 1 if one or the other, if there's an odd number. The next one I would test would be 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. I really encourage you to get used to testing in order. In your labs, write it down. Don't say, oh yeah, I remembered that was right.